Well, then we're fitting in.
So it says on your schedule, but I'm not sure if you reviewed it. Do we have class the week after?
No class. And I'll be sending out more emails about that. I got another meeting.
What
week
handout
after.
was homework 12 on?
Homework
Was it on
12.
the eve? Oh.
Yeah.
Haven't looked at my junk mail, that's why.
That's the one that's due Friday?
Yeah.
And did I not print out ever?
I
Just
you
emailed it?
In the email, I think you mentioned I'll give you the printout on Monday, but I don't.
And then
think it was
and then I
on,
forgot.
Yeah.
Yeah. All right, I'll put homework 12, I'll print out tomorrow, because most people aren't gonna start till tomorrow anyway, right?
That's good. I'm not crazy. I'm not the only one who didn't find it in here.
But I did email it, so look in there, but I'll try to make sure I do that tomorrow. All right. Conference rooms up there are freezing, but this room is fine. Did everybody get my email about how I had a brain fart on like recording everyone's homework 9 scores? So if you could maybe after lecture come by and like show me what your score was. I mean, I kind of remember what most of them were, but I don't want to write them in like based on what I kind of remember. That would be dumb. So if you guys do that, I appreciate it. That was definitely my fault, so I apologize for that. So eager to get into those like.
Give us all 10s.
I think people in general did well, so, I mean, I could give you all 9s, and I think I'd be within, you know, a sigma on most people, so. Okay, so we were talking about principal axes. No, we weren't. We were talking about moment of inertia tensors, yeah? All right, so we just calculated a giant moment of inertia tensor for the cube when rotated around one of its axes, right? Okay. So we didn't quite get to yesterday, and we might as well finish it. Let's go ahead and try to calculate I for a solid cone. Right? So I'm going to set this up like this, x, y, z, and the cone's going to look like this. It's got a height, h. It's got a radius, r. Okay. So the question is, what's the moment of inertia tensor? How do you calculate it? So what happens to Jonah? First of all, what are the elements of the moment of inertia tensor? Right, what does it look like? Yeah. We got the diagonal elements XX, YY, and ZZ. And then there's XY, XZ, YZ, and then conjugates over here. Okay. So, you want to remember how to calculate each of these?
For the diagrams.
Yeah, integrals. What was it for IXX?
M times, or rho times x squared plus y squared, or no?
Y squared plus Z squared. That's pretty sure, yeah. Yep. So let's start there. No, sorry. Looking at my notes. Let's start with ZZ, because that one's easy. Why is that one easy?
It's the axis.
Yeah, it's symmetry. That's the Z. Everything's symmetric around the Z axis, so this is going to come out more straightforward. X squared plus Z squared. And in fact, we can just call that. Let's call that little r squared, where little r is the distance from the axis. Then we can integrate this in cylindrical polar coordinates. In which case, just look at a density, that's going to be on the outside. Okay, we're gonna have an integral in z from 0 to h. We're gonna have an integral in, let's call that phi. I like that better than theta. That's gonna go from 0 to 2 pi, yeah? But the volume element is gonna be r d phi, right?
Yeah.
And then we're gonna have this integral from 0 to big R in R. And what's inside? R squared. Except that this R, you know, is in the integral. So isn't that? Does that seem reasonable?
Do we need to do,
Yeah, question.
to me
You
that
can
looks-
blur it, you don't have to hold your hand up
That
around
looks
here.
like a cylinder. Would you need to say, have R in terms of Z or something? Because it's a line.
Yeah, no, you're right, yeah. This R isn't just R, it's R, we'll call it R outer as a function of Z. I like that. Yep, I think you're exactly right, okay. In fact, what is R outer as a function of Z? Well,
R over H times Z.
yeah.
Right.
It needs to be 0 and 0. It needs to be R at H. And it needs to be one in between. So that one's pretty straightforward. So we'll call that R over H. Okay. I have no idea if this is following what I did in my notes, but it should work. It probably won't, but it should, you know. Okay. All right, so we've got a row on the outside. And we've got, let's do the interior integral first here. We got an integral there. It's from 0. I take it back. The integral in phi is just going to be phi integrated from 0 to 2 pi. It's going to be a 2 pi, right? Let's dispense with that. We got 2 pi up front. Okay, we got an integral from 0 to h dz. It's going to be left over. In between, we have an integral of r cubed dr. It's going to be r to the 4th over 4, yeah? Evaluated from 0 to r over h times z. So this is going to be r to the 4th over h to the 4th times z.
The fourth. Yeah.
Yes, z to the 4th. You are correct. All right, we got one more then. R to the 4, h to the 4. Let's just stay out here. And then we just have an extra h, you know? Which becomes h cubed. Was that too simple?
No, it's,
Yeah, okay,
yeah,
yeah,
it's
that was-
1/5 z to the 5th.
Yes,
so-
that was too simple. Okay. So this is 4 still. Okay. You're right. So this is z to the 5th. So h to the 5th over 5 is what that's going to be. Yeah, that's more rational. Okay. This is going to become then. Interesting. I don't like it. There's only an r to the 4. But
R to the 4 times h.
But there's an h.
So-
You're right. There's the units still work out. There's still 5 lengths. So you're right. I think we're still good. Pi rho over 10 r to the 4 times h. All right. So usually we do this in terms of the mass of the cone, right? Anyone know what the formula is for the mass of a cone?
1/3 h.
R squared. Yep, I think that's right. I had to Google it yesterday, but I think that's right. It's 1/3 m 1/3 h pi r squared. Yep. Okay, so
That's the volume.
times rho.
Yep.
Okay, so this is gonna pull out an r squared, an h, and the pi, and the rho. And guess we'll make this 3/30. So we can easily take the 3 out. And now IZZ is gonna be what, 3/10 m r squared. That look right?
Yeah.
Got two r's left, and then the 1/3. Pull that out with the pi rho, 2 r's and an h. Yeah, okay. Well, that was a pain, but it was doable. This also comes out in the same form that you guys recognize, right? As a moment of inertia. Some coefficient times mr squared, which is what you want. That's what you want to look for. That's what you should expect anyway. Okay. Now, did I actually do the other integrals, or just say that they were symmetric and call it good?
Are they symmetric?
Well, I actually did them. Okay, I did them. Okay, the off axis ones here are 0 because they're symmetric. However, the other ones are not. So let's do YY, say. YY is going to be volume integral of rho x squared plus z squared. Yeah, oh, I did XX, doesn't matter. Same thing. Okay. And let's pull this out. Oh, I just skipped to the answer there, didn't I? Unhelpful. Yeah, that's not entirely obvious where that comes from, is it? I think to me. All right, let's try it. Yeah, so an advantage is if we're doing this in polar coordinates, for instance, cylindrical polar coordinates, typically there's going to be r terms and there's going to be z terms, and those are going to be separate. In that case, we can separate this out into 2 separate integrals. 1 over x, so that's to be over the whole volume, and 1 over z. Yeah, I was going to say, that seems to be remarkable efficiency in my notes there, doing that in 1 line, but I think it's more than that.
Less than that.
Yeah, it's not efficiency, it's, I think I skipped to the answer. Okay, I'm gonna skip to the answer again, because I actually, what I really want to get to is the principal axis stuff. I think we could figure this out. And I think I would do the integral back in the same cylindrical polar coordinates, but we'd have to do a substitution for x, and it's probably going to involve then x is going to be r times, cosine phi or something, right? And we'd have to do the whole thing. I think it's doable, but I'm going to trust my notes here and say that if you did that integral, you'd come to the answer 3/20 m r squared plus 4h squared. Why does it depend so strongly on h?
Because h is your distance away from the axis.
Yeah, since you're actually rotating around the point here of the top, there's way more mass out here than there is down here. This, in fact, is starting to dominate the answer. Because yeah, the r factor is, yeah, it makes a difference. I mean, fatter is going to be a little further away. It really starts to matter, of course, as r is bigger than h. But if r is smaller than h, it's really the h that's going to make the big difference. Okay. In that case, if this is symmetric, which I've So, because of the symmetry, these off-diagonal elements are going to be 0. I can leave that as an exercise for the watcher. If you guys want to try that out. But if you do those integrals, they should come up to be 0 because they're all over, you know, for instance, it's going to be, you know, and the IXY is going to be a function of x times y, right? And that is going to be symmetric all over because it's symmetric around the z-axis. The trickier ones might end up being in z, but they should come out okay too because we're actually along a principal axis there in z. Okay, so in that case, the answer, if this is what I were to ask you, is that this matrix, this tensor looks like, well, there's IXX here. Common denominator here, 20. So in that case, the 20, this becomes a 6. This becomes a, we can pull out another 2 in that case. And now let's just leave it. This becomes a 3 r squared plus 4h squared. This is a 3 r squared plus 4h squared.
What, isn't it in the upper left corner XX and in the bottom right corner ZZ? Have it switched?
Yeah, absolutely, you're right. And I can't pull a 3 out here.
No, you can't pull out the.
So I can't
R
pull out the other
squared,
guys.
Right?
The 2 should be in the bottom.
Yeah, you're right. And this becomes 3r, except the 3 got taken out already. So this is just r squared plus 4h squared, and then this is a 2r squared. Yeah?
Yeah.
I like that better. Yeah, that's what I have in my notes. Okay, good. Okay, so this is where we're going to get into what we're going to talk about today, even though we're halfway through this lecture. This is a much prettier moment of inertia tensor than the one that you were subjected to with the cube on the axis. The reason for that is that all the off-diagonal elements here are 0. This is the desired case. In fact, so if the tensor is diagonal, then the coordinate system axes are principal axes. And this is what we're going to talk about all day today. How to make your matrix look like this so it's not a pain. It turns out principal axes are special. Okay? You can rotate things around whatever axis you want, but if you rotate it around a principal axis, you are being special. And this is a desirable quantity. In fact, the reason obviously this is desirable is that if you have a diagonal matrix like this, then our old, you know, if you are looking for L equals I omega, this is true if you are in fact rotating around one of those principal axes. So this is one of the reasons that we lied to you in Physics 211 and told you that this was always true. And that's because it's frequently true. It's true if you're rotating around a principal axis only. So in fact, this is something that we look at for planets and stuff, okay? I was at a talk in, this is 2 trips ago, when I was in Europe, okay, at the European Planetary Science Conference. We have a spacecraft that is now orbiting the asteroid Ceres, which is the largest asteroid in the asteroid belt. This thing is, it's the largest asteroid in the asteroid belt. It's about 1/10 the mass of our moon, so about 1/2 the radius of our moon. And one of the first questions is it rotating around one of its principal axes? The reason you ask this is that if it is, then all the subsequent calculations become easy because you can assume that the angular momentum is straight up that principal axis, And once you calculate the volume of the body and what it's doing, you've solved the problem, and you don't have to ever worry about that again. You can program it into a computer that it's going to be rotating at a given rate, and if you want to know what side of series is facing you on a given date and time, you can just plug in the rotation rate, and you know what axis it's spinning around, and you solve the problem. It's just easy. If it's a non-principal axis rotator, your life sucks. There are just about, I think the only non-principal axis rotator that we've really identified, as I said on Monday, is this weird moon of Saturn, Hyperion. It's the real problem child of the solar system. Everything else is mostly a principal axis rotator, and really the reason for that we'll get to probably in astrophysics, but it has to do with it has to do with dissipation essentially within the body. Okay. Yeah.
So if it's non-principal, does that mean angular momentum isn't written this way, but it's still conserved?
That means this is still true. This is always going to be true. But if it's a non-principal axis rotator, then omega has elements that aren't along one of the principal axes, in which case you have to do this. You actually have to do this full matrix multiplication. And even for a diagonal matrix like this, you're not going to end up with the angular momentum being parallel to the rotation vector unless you're only rotating around one of those three axes. So, right, let's do an example. If you were to be cruel and decide to rotate this thing around some axis 1, 1, 1, right? So let's set omega equal to 1 over root 3 times 1, 1, 1 again, like we did for the cube. Right? This was the principal axis for the cube. Turned out great for the cube because we ended up with L parallel to the rotation vector. If you do that here, you're going to end up with, not I, but L, which is equal to I times omega. You're going to end up with 3 over root 3 times 20 times m. Okay. It's going to be, well, pretty easy. It's going to be r squared plus 4h squared, r squared plus 4h squared, 2r squared. So unless r squared is equal to, unless r is equal to 2h, right, if r were equal to 2h, each of these would be the same, right? Yes. If r were equal to 2h, all these would come out same, and then L would be parallel, the angular momentum would be parallel to the rotation vector. But in general, L is not going to be parallel to the rotation vector. He's going to be something nasty. And even in the even though there are principal axes, because you're not rotating around one of them exclusively, you're going to end up with a nasty situation. Okay. So we're going to talk about the rest of the time here is how do you find these principal axis things? One cool property that we need to say from the beginning is that every rotating body has principal axes. So for every rotating body, you can come up with, a motion inertia tensor such that all the off-diagonal elements are 0. If you just choose the axes right, we call these lambda 1, lambda 2, lambda 3 in that case. Okay. So this, you can find one of these in any case. How do you do that, though? Here's what we're going to talk about. How do you find that? All right. It's that, okay, you note that if we want to find, right, a situation where L equals I omega is equal to just some scalar times omega, because in that case, the angular momentum is parallel to the rotation vector. So this is, you guys all take a linear algebra, right? You guys probably know this better than me then, because I haven't thought about this. Oh, that's not true. I do use these fairly often. But so this is one of those eigenvector equations, eigenvalue things. So if you choose your vectors right, your eigenvectors, for a given set of 3 eigenvectors, there will be a unique set of 3 eigenvalues. And those vectors will be the principal axes around which you can rotate this thing. And the values will be the moments of inertia, the products of inertia, around each of those vectors. So let's show you how to do that. Basically, this is true if you can sort of rearrange this, figure out that if you take the determinant of I minus a 1 tensor, so a diagonal tensor, this is equal to 0. This is how you find it. This is the characteristic, called the characteristic equation. I'm running out of board space, but there you go. Okay. So once you find I around whatever set of axes you've elected to implement, you can then figure out which principal axes you should have used, what the principal axes of your rotating body are, if you plug it into the characteristic equation and figure out the roots to get your eigenvectors and eigenvalues. So let's do that. It's too easy for the cone, so we're not going to do the cone. Too easy. Let's go back instead to our nasty cube rotated along its side, because that's nice and hard. The problem with the cone, of course, is that it was the tensor already came back diagonal, right? It's already diagonal, so there's nothing to do. So let's find a hard one, or at least not a hard one, but one that has off-diagonal elements, so there's a job to do. So we're looking at the cube. Ugh. All right, whatever. So you look at the cube. Was the sides were length A, right? And I have here in my notes that in that case, the moment of inertia tensor that we calculated on Monday was it had a bunch of non-diagonal elements, right? You don't remember this from Monday? It wasn't that long ago, guys. Okay. In that case, I said you want to take the determinant of this equation, of this the resulting matrix there, I, moment inertia tensor, minus lambda. You should be able to get the answer. So let's do that. Take I minus lambda times 1, then the moment inertia tensor, the characteristic equation, we'll just call it that, characteristic equation is equal to ma squared over 12, blah, 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 8 minus lambda. Is that right? Yeah. 8 minus lambda, 8 minus lambda. These negative 3's are still there. And that is equal to 0. Okay? Well, let's get rid of this because this is boring. That's equal to 0. But let's go ahead and take the determinant of that, see how far it gets us. So that's going to be 8 minus lambda cubed, right?
Yeah.
Minus 9, 8 minus lambdas. No, minus. 9 minus 9. So this is, sorry. Subtracting I think it, yeah, I think you're right. 3 minuses should lead to a minus. And that's gonna be, okay, so the next one is gonna be plus 9 minus 27 and then minus 9, 8 minus lambdas. And the last one's gonna be another minus 27 and another minus 9, 8 minus lambda, I suspect, right? Okay. Well, I came up to something much simpler in my notes, though. Exactly. I'm sure it simplifies down, but there you go. All right. Kind of nasty as it is, but certainly there's. Yeah, that's weird. He's not. Okay. Yeah. I think the only way to do this is to absolutely multiply it out the brute force way, and then start grouping like terms and put things together. And according to my notes, everything I skipped is step 2. If you do that, yeah, you will end up with. Sorry, let's put this over here. Minus 27 minus 9, 8 minus lambdas. Equal to 0. Okay, fundamentally, it's just a cubic equation, right? The highest order in lambda is 3. So, how many solutions to this equation are there? 3. There are 3 solutions to this equation. So let's go ahead and do that algebra. Okay, imagine we did all that algebra. It comes out to, if you group the like terms, it comes out to 2 minus lambda times 11 minus lambda squared equals 0. In which case, there are 3 possible solutions, right? There's lambda 1, which is 2. And these 2, because it's squared, kind of lose that one. So there's 2 others, lambda 2 and lambda 3 are both equal to 11 in that case. And in this case, well, my notes actually left this in front of it. So this became 2 ma squared over 12. So this becomes ma squared over 6. And this becomes 11 ma squared over 12. Okay, well, these are the 3 answers. All right, these are the 3 total. These are the 3 eigenvalues. So these are the moments of inertia around the 3 principal axes. But what are the 3 principal axes? Let's figure that out. All right, so to go back. Yeah, we got 2 of these. All right. So we start plugging this back in. So to figure out the first principal axis, we plug in lambda 1 into here. In which case, put this ma squared over 12 back out front here. 1/6 of that is going to be 2, so this is going to become 8 minus 2. So the equation is now going to become 6, or sorry, this tensor looks like this. And in order for, right, if L is equal to this times some vector, this is what we're looking for. This is going to end up being the eigenvector we want. What do I call him? Okay, E1. That's going to be vector eigenvector E1. In order for this to be true, let's see, this is going to become going to be 6 omega 1 minus 3 omega 2 minus 3. Wait a minute, I could have simplified this from the beginning. Okay, let's make this a 4. Sorry about that. All right, that's much easier. Instead of 6s and 3s all over the place. Now, 2 omega 1 minus omega 2 minus omega 3, omega 1 minus omega 1 plus 2 omega 2 minus omega 3 minus omega 1 minus omega 2 plus 2 omega 3, multiplying this out, needs to be equal to 0. Right? No. Yeah, that's what I have. Yep.
Hey, you know what's equal to 0? Or on that axis?
Okay, you're right. This is not the angular momentum that we're dealing with, right? This is the characteristic equation I minus lambda times 1. And that's what has to be equal to 0. Sorry about that. So this is I minus lambda times 1. That's equal to 0. Okay. So this is essentially 3 equations, 3 unknowns, right? If the result of this is equal to the vector 0, then there's 3 equations, the one in x, one in y, one in z. Those have to all be 0. How can you satisfy that?
Well, if they're all 0, satisfied.
Okay, that's a trivial solution. Yeah. what if they have you know, you're looking for a unit vector, so it has length 1 or whatever. Right? Okay, so cheating and looking at the notes, you could actually solve these 3 1 1 1. Yeah, right. Okay. So if omega 1 is equal to omega 2 and omega, if they're all the same, then this top is going to be equal to 0. You always have a plus 2 and a minus and 2 separate minus 1s. So this is true. So this eigenvector 1 here is going to be equal to 1 1 1 normalized. Which we already knew, right? Remember when we rotated around that particular vector, we happened to find this by dumb luck when we were doing the problem before, but we've showed how you can, in general, derive what the answer should be. All right, let's now look for the other principal axes. Looking for E2 and E3, we're going to take I minus lambda times 1. In the case of this other lambda, which is 11/12. So we'll go ahead and leave the ma squared over 12 out front. So that becomes 8 minus 11 minus 3, huh? Huh.
Man.
So that's equal to vector 0. Yes, we can pull negative 3 out. But it almost doesn't matter because it's all going to go away anyway. The point is, you're going to end up with 3 equations here, which are each equivalent to equals 0, right? Once we pull the negative 3 out, these are all going to be 1s. Each line is going to be separately equal to 0. They're all the same. This is useless to us. This doesn't tell us anything. All that means is that, and this is all you could, if you knew what you were looking at, by the fact that this is a squared here and that these 2 moments of inertia are the same, you can tell that the other principal axes actually do not matter. They're not unique. They can be anything you want. So long as they are perpendicular to E1. And you can get into exactly why that is, but when you go through, you'll find that in order for this to be true, is how there's a set of these that, for which this is true, a set of omegas. However, all of those sets are all perpendicular to E1. So E2 and E3 are indeterminate but they're perpendicular to E1. So this is always true. There's 3 principal axes around every object. This one happens to have some symmetry. The cone happens to have some symmetry. You can have some awful, most convoluted object you can imagine, like that comet. Churyumov-Gerasimenko. Thank you. Yeah, you got it. You were on top of me. You beat me. So there's this comet that was visited by the European Space Agency, and I was at these talks just this week where they hate to admit doing it, but they refer to the different parts of it as the head and the body of the rubber ducky, because this is what this comet looks like. Okay. Weird. What are the principal axes of this thing? It has 3. First of all, they're all perpendicular to one another. It turns out the principal axis is this one, heading straight down. Actually heading. So if you imagine the rubber ducky sitting there, this is why we use this analogy. Okay. You have the rubber ducky. You take the rubber ducky's center of mass, and you draw a line sort of from left to right. That is the principal axis. And so this thing is spinning head over body out in space. It is spinning. Even this crazy comet shaped like a rubber ducky, we have to figure out what its principal axes are. And this one happens such that it is spinning around its principal axis. And it's spinning around its principal axis that has the greatest moment of inertia. And we'll get to why that is in astrophysics. That's a little tricky. So, in general, this is the formula for how you find the principal axes once you have it. First of all, you calculate your initial moment of inertia tensor. Let me write this down. Okay. Here's the recipe. 1. Find the non-diagonal tensor. Once you have that, calculate the eigenvalues from the characteristic equation. Step 2. Step 3, plug the various eigenvalues into the characteristic equation to find the principal axes, the 3 principal axes. This is this times, sorry, go back. All right, well, so the characteristic equation here is I minus lambda n times 1, because there are going to be 3 of those, times your that's what you're solving there. And this is, in general, going to give you 3 equations, 3 unknowns. And you're going to have to figure out what specific vector, omega 1, omega 2, omega 3, is is going to give you those three, is gonna give you these three such that you can come up with what your individual principal axes are. Easy, right? Okay, that's hard. I know that's hard. But the glorious thing is once you get into this state, then you have a diagonal moment of inertia tensor and your life becomes simple from there on. Okay, but this is the hard part. You do this hard part up front, you figure out what the moment of inertia tensor is, you figure out what the eigenvalues are, the lambda 1, lambda 2, lambda 3, that correspond to the products of inertia in the diagonal case, when you calculate what three axes those correspond to. And the cool thing is, everything has three principal axes, even if it's a rubber ducky, okay? It does not have to be a standard shape or a symmetric shape. Any nasty object, every nasty object, has these three principal axes. This is how you find them. Okay, tomorrow we're going to talk more about how to use these and what we're going to do with them, what they tell you, you know, fun stuff like that. All right, see you then. Thanks for coming, you guys. I appreciate you guys coming to these extra lectures. I know it's a pain, but this is your penance for having 2 weeks off. You got to make up for it somehow.
This next semester will be a similar style as this one.
In what sense? In me going away all the time?
Yeah.
I do not have as much travel. This was a bad semester, okay, I have to say. This is by far the worst travel, the most travel I've ever had for any semester. Right now, I can tell you right now what I have scheduled for the spring. I'm skipping the usual March conference, so let's see, I'm gone for Europa assessment for 1 day in January. I got OPEG 1 day in February. Got a conference at the end of March. It's going to be 1 day. I only have 3 days I'm scheduled to miss so far. That is like the fewest I've ever had since I've been here. And this semester is the most I've ever had since I've been here. So if you go to if you take both this and astrophysics, on average, you'll get it about right. But I definitely did not plan to be gone this much. It just worked out that way.